So now that we've seen that derivative as a function, let's move on to page 2 and talk about the derivative graphically. So what we did is just calculated the derivative algebraically using actual functions and x's, and now we're going to look at how you can figure out what the derivative is from a particular graph. And we're going to start by doing an exercise. We've got two graphs here. One's the dotted line, one's the solid line. And I want you to see if you can figure out which one of those is the original function f and which one is its derivative f prime. And I give you a hint here to look for places where there's positive slopes corresponding to positive y values in the other graph. So take a minute to try that out. If you're completely flabbergasted, then just unpause the video and see what I have to say. But for now, pause the video and try to do exercise 3. Okay, so there's a couple things to look for. I say look for places where a positive slope in one graph corresponds to positive y values. So if you have a function f and it's got a positive slope, then that means its derivative f prime will be having positive values at that spot as well. So I look here and I say, oh, my solid blue graph here, it has positive slope all the way along here, and all that time my dotted line also has positive values. But here my dotted line has positive values, and those correspond to positive y values for my solid line. But when I get to this area right over here, the dotted line has a positive slope in terms of the tangent line to that spot would be a positive slope. But my y values down here for the solid line are negative. So that means the slope for the dotted line does not correspond to the solid line, but the slope for the solid line does correspond to the y values of the dotted line. So this would seem to imply, my first guess is that my solid line is my f of x and my dotted line is f prime of x. And there's another thing we can look at that will help us identify which one is which, and that is to look for when the slope of the tangent line is 0. So I notice that at this point I would have a tangent line that's horizontal, and I would also have a tangent line here that's horizontal. And both of those horizontal tangent lines on the solid correspond to when the dotted line is crossing the x-axis. So a slope of 0 here corresponds to a y value of 0 there. And that's also a very clear indication that your solid line is f of x and the dotted line is f prime. And notice that in between these two 0 values in my solid line, these are all negative slopes. Those correspond to negative y values. And then over here, I would have positive slopes again. I'm going uphill. Those correspond to positive y values in the dots. All right, now example 4, it says, given the graph of f, sketch the graph of f prime. I'm going to make this a little bit larger for us. And the idea here, there's a lot of correct answers. I'm going to start by just putting in some x values here that correspond to what I've got over there. So -4, -2, here's 1, 2, 3, 4, 5, 6, 7. And basically what I'm going to do is, as I come along here, when I look at the tangent line to the curve at these values right here, my tangent lines all have negative slope. They're all going downhill. So that would mean that my derivative function would have negative y values because it's corresponding to where we're getting negative slopes over here, and it would continue to have those up until when x is equal to -1, because at -1 that's where at the bottom of this hill here, bottom of this valley, I'm actually getting a horizontal tangent line. So maybe this looks like, I don't know, something like that. So I'm getting all negative values and then they cross 0 here. And then as I come along here, I'm going uphill. These are all positive values. So that would give me, sorry, positive slopes give me positive y values over here. And I continue to get those. And they just get steeper and steeper. And then at this spot here, it looks like the tangent line actually goes horizontal. And then it starts slowing down again. It's still positive all the way through here. So this is going to come down. And when I get to a x value of 3, it actually completely flattens out here and stays flat until about 4. So this is going to come down here. At 3, it's going to hit 0. It's going to stay there until about 4. And then my slopes start going negative. They're going downhill. So this is going to go down. And it's kind of unclear what happens here, but it looks to me like as I get close to that point, I'm getting a slope of maybe, I don't know, -2 or something. And then it just sort of stops. I'll put an open circle there. And then what happens here, well, this is actually a slope. That's just a line. And you can do rise over run to see that the slope there is 1. So maybe I'll put a y value here of 1. And from that point on, I'm just getting a slope of 1. Along that straight line, my derivative is always going to be 1. Now, there are 2 points on this graph of f prime where something strange happens. And I think it's pretty easy to see that they occur at x equals 1 and x equals 5. And the question is, what's happening in the graph of f prime and what's happening in the graph of f? So at x equals 1, let's shrink this down a little bit. So at x equals 1, we actually have this spot where the tangent line goes horizontal. So if you want to get the, sorry, tangent line does not go horizontal. The tangent line goes vertical. I'm talking about this spot right there. The tangent line actually goes vertical. And vertical slope is undefined. And why is it undefined? Well, remember, slope is rise over run. And we're getting a rise here. It's going up, so it might rise up, say, 4 units. But it doesn't go anywhere to the left or the right, so the run is 0. And dividing by 0 is undefined. Or, as we like to think of this, you can think of that as going to infinity. Okay, so this slope is actually going to, either positive infinity or negative infinity. And since we've got positive slopes on either side, the way that shows up is positive slopes on either side here, both of them going to infinity. So this, let's say this way, this implies that f prime of x goes to infinity, which means that in the f prime graph, we've got a vertical asymptote at x equals 1. So I'll draw that in. There's my vertical asymptote at x equals 1. So this is only on the f prime graph, and it also means that f prime of 1 does not exist. So at that spot where you got a vertical asymptote, the functional value does not exist. Now how about at x equals 5? Well, on our function f of x, it has a sharp point, right? You may remember, I can erase a little bit of that so you can see the sharp point there. And what does a sharp point mean? It means the slopes are doing something on one side and the slopes are doing something different on the other side. So this means the slopes are doing different things on each side. Which means that we're basically getting a discontinuity. Our limit from one side is not the same as our limit from the other side. that's a discontinuity for f prime of x. Okay, so notice our f function is continuous, it's got a sharp point, and what that means is that our f prime is actually discontinuous. So we've got a discontinuity, and f prime of 5 does not exist. So what's happening here, why does f prime of 5 not exist? We can't actually tell what that derivative would be at that point where there's a sharp point, because from one side we think we're going here, and from the other side we think we're going here. So there's no way to define what that limit is. And we have a term for this mathematically. We say a function is differentiable if the derivative exists, and on an interval, so that's differentiable at a point, we're differentiable on an interval if you're differentiable at every point there. So for example, let's just talk about this one right here. Example 4, we would say that f of x is not differentiable at x equals 1 or x equals